Welcome.
Welcome. Welcome to Hopkins on the Hill.
Welcome to Hopkins on the Hill at home.
Hello, I'm Congressman Dutch Rubersberger, and I'm grateful to participate in this year's Hopkins on the Hill at Home event, although I wish we were able to celebrate together. I always tell people how lucky we are in Baltimore to have Johns Hopkins, a world-class institution, right on our doorstep. Aside from keeping Marylanders healthy and treating over 250,000 second district residents, Johns Hopkins is an integral part of our economy, employing over 12,000 second district residents. They also empower the next generation of leaders to excel, investing more than $9.2 million in annual financial aid for students in my district alone. Johns Hopkins performs cutting-edge, life-saving work each and every day, and for that, I'm very thankful. I promise to continue fighting for every dollar I can to empower Johns Hopkins to keep leading the way in global medical research, innovation, and treatment.
We approach our research with a simple philosophy of seeing, understanding, and controlling the mechanisms that are at play when we defend against weapons of mass destruction. We launched the consortium in July of 2020, and we are now investigating how various materials and chemistries both perform and evolve within the extreme pressures and temperatures and radiation that are associated with both agent defeat and nuclear blasts.
This experiment is helping us to figure out how engineered metal powders and composites like aluminum react. The powder is coated on the wire, and then using a power supply, we heat up the wire, which in turn heats the powder until it ignites and burns in the surrounding air. We can use a high-speed video camera, pyrometer, or other optical devices to determine the time and temperature of ignition. I don't think we ever want to be in a position where we have to safely destroy extreme and hazardous materials. But we also know that this happens when we consider the recent chemical attacks in Syria. My work is going to help protect humans and our environment because we're finding new innovative ways and strategies to prepare, test, and characterize metal reactive systems that provide high heat and release combustion products that can kill these harmful organisms like anthrax and destroy toxins like sarin while they're burning, all mitigating the risk of exposure to the environment and to humans.
We have a broad range of programs that are designed to develop a diverse workforce for future generations. These programs include summer internships for high school students, full-year internships for undergraduate students that link closely with Morgan State University, and finally, travel fellowships that allow PhD students and postdocs to spend up to 4 months at national labs to gain critical professional experience. The Material Science and Extreme Environments University Research Alliance is funded by the Defense Threat Reduction Agency and spans across 18 different institutions that include universities, national labs, and companies.
Welcome to Hopkins on the Hill, and a very special thanks to Maryland's 2nd Congressional District Representative Dutch Rubersberger for his message. So today, we will be speaking with Hopkins folks associated with 2 major research programs, the Materials Science in Extreme Environments, or MSEE, and the Materials in Extreme Dynamic Environments, or MEED programs. Both research programs are under this umbrella of the Hopkins Extreme Materials Institute. The goal of these 2 federally funded research programs is to really develop technologies to keep people safe. So we will think about Americans as well as our fellow global citizens. So first we're going to dive into the program MSEE, and then we're going to pivot and we'll talk more about MEED. The video you just saw gave a little bit of background about MC, and it featured Dr. Tim Weihs and Dr. Kerri-lee Chintersingh, who we have with us today. So welcome, Tim and Kerri-lee. Thanks for being with us.
Thank you for
Great.
having us.
Yeah, Kerri, thanks. It's good to be here. Thanks for having us.
So Tim, let's start with this landscape of weapons of mass destruction, or WMD. Where are they in the world right now? And can you remind us of a recent use of WMD?
Sure. There's actually two that come to mind. Certainly a recent use Kerri-lee had just mentioned in Syria back in 2018 and earlier. Unfortunately, there have been uses against civilian populations of chemical agents, chemical gases such as sarin, mustard gas. They're around the world. They are used, unfortunately, in situations where civilians are harmed and killed. The other one that I would note is the risk of nuclear weapons. And we hear recent decisions and discussions with North Korea, which is improving its ability to launch these weapons. So I think that risk, many would say, is growing.
So then what is the goal of the MC program as it relates to these weapons of mass destruction?
That's a great question, Kerri. So there's really two slightly different goals depending on which of the weapons we're talking about. In case of the chemical agents that we mentioned, our hope is actually to develop technologies that will be able to neutralize those agents, whether it's a bioagent or a chem agent, before they're used. So it's really trying to prevent an attack. In the case of the nuclear weapons, our goal is not as much try to prevent the attacks as to understand what happens in the case of a nuclear blast, so we can help mitigate some of the consequences. So understanding the radiation, the blast itself, the shock wave, as well as the evolving chemistry. So if we understand that, we can help mitigate some of it.
So with these two kind of separate goals of prevention through neutralization and mitigation for nuclear weapons, right, there must be different mechanisms then that you're relying on for these different goals. Can you talk a little bit about those mechanisms?
Sure. So we really try to understand what's happening. So we're focusing on this from a scientific basis. So we're trying to develop the science that will allow the Defense Threat Reduction Agency, DTRA, to help design programs and weapons that will help neutralize or mitigate. And so in the case of the agent defeat, we're really trying to look at combustion itself and understand what are the processes when metal powders actually burn in air, and how do they produce heat through that combustion process. On the nuclear side, we're worrying about what is the effect, say, for example, of a shock wave hitting a material at very high speeds. Can we simulate that? Can we actually measure that?
Interesting. So with this idea of combustion and needing this heat from combustion, Kerri-lee, the experiments that you showed in the video were about combustion. Can you talk a little bit about your work and the key factors that you're looking for in the use of combustion to neutralize chemical agents?
Sure, no problem. So my primary focus is on studying combustion of metals. And so when we think about metals burning, we're thinking about very high temperatures released. There are several factors that can affect how well these metals are burning. So for example, their particle size, the oxidizing environment that they're in. We're thinking also in just the typical metal macrostructure, what chemistries are there, like different metals burn at different rates and in different phases. So we're trying to explore all these different parameters that can affect how fast the metal burns, how much heat is released as the metal is burning, and that in turn, and the type of products that are being generated as the metal burns too, because all these tie in to affect how well they interact for that targeted application, which is to neutralize this chemical agent.
So when you're talking about this, you're talking about in-lab experiments where you're looking at these different influences on that combustion level. But how do you take something from an in-lab experiment where you're able to control a lot of those variables and translate it to the field where you could be somewhere in the world needing this information, this science to actually neutralize or mitigate a weapon of mass destruction? How do you make that translation?
So really all the lab or controlled environment experimentation is used to build these models or to translate into these models for these weapon codes that NUTRA is designing. So for the application side of things, or fundamental science experiments are going to be feeding into that application side. So we're taking things from a single particle level, trying to understand things on a controlled scale, and then using that to feed into our computational fluid dynamics, which will account for the environmental changes, and that can also account for the larger scale experimentation.
I see. So you're investigating how all those factors might be related. So when you do translate, you're ready. You're
right.
On the scheme.
So ideally, when you're designing for applications purposes, you'd like to have like a single simple equation that pretty much describes how these metals are burning. And we are doing the experimentation to develop that equation essentially, or to develop that model so that it can be somewhat of like a plug and play for the application.
Interesting. So you essentially have to really think through all the different factors, the range of potential variables for those factors in order to kind of get this equation together to figure out the temperature at which you need to burn.
Yeah.
Do you have, what in your lab, what tools are you using in order to kind of harness all of that information and really measure closely?
So we have several tools. One of the examples that I showed in the video was just using something like a simple hot wire filament to ignite these powders. That will tell us pretty much what are the minimal ignition thresholds, because that's important for us to understand how much heat input is required to get these powders going to start burning, right? We are also in the process of designing a customized chamber that will allow us to not only see how these powders are burning in air, but when we introduce a simulant toxin to sarin, for example, DIM, how does the metal particles when they're burning interact with the simulant? So we're also exploring different ways of igniting these powders, for example, using a plasma or a laser. So these are all just different experimentation that is going on in the lab, because these will help to tune how well the particles are burning in air, and how they're igniting. We can establish what the temperatures, the pressures, that kind of stuff, which will all lead into developing these models.
So it's interesting to say you're designing the chamber, right? So that's not something you can purchase, or it's already made somewhere. That has to be kind of a conceptualization to a customized kind of secure space in order to have some sort of combustion going, and then introduce the agent in order to really get kind of that experiment going to see exactly how those two are interacting. Sounds very both intellectually intensive, but also resource intensive. So Tim, bringing you back in for a minute, how does the MSEE Center really secure those resources needed to conduct these experiments, or design chambers needed for these types of experiments to be done safely, and then eventually, translate this knowledge into neutralization of weapons of mass destruction in the real world? Where do those resources come from?
Sure, happy to share thoughts on that. So, Kerri, they come from the federal government. So a number of years ago, I think it was 2018, they came out with a broad agency announcement. They said they wanted to establish, DITRA wanted to establish a center focused on materials in the extreme environments associated with weapons of mass destruction. And so I worked with others to pull together a team of 40 PIs across 13 different states and many organizations. And we've pulled together our concepts and our plans and put in a proposal that fortunately was successful. And DITRA now is committed to funding this for the next 5 years, but also beyond that, potentially for another 4 years. So our hope is a total of actually 9 years. And what that does is it gets these researchers, us collectively, working together in a very cooperative manner. Very often we're funded as individual researchers or principal investigators. And sometimes we feel like we're in competition with each other. But in this case now, we've been brought together to work, as a team, as a big team. And that really builds many efficiencies and lots of collaborations into the system. So that's worked really well. And we also, Kerri-lee was talking about her experiments and trying to confirm what's happening at that single particle level. We also work closely with the folks at national labs. These are both the defense labs and the Department of Energy labs, or DOE labs. And they're wonderful partners. We have some of them on our team. But as we develop knowledge, as we develop models, we try to transition those to those federal labs as well, so they can scale up and do tests at larger levels.
So you mentioned DITRA, and just for everybody who doesn't speak in acronyms,
Sure.
as we tend to, that's the Defense Threat Reduction Agency, which is your main funder. But I want to go back to what you started with. that you pulled together 40 collaborators across 13 states.
Right.
So tell me about that. Is that like you're calling up old friends? You guys have meet for a beer, or is that, how do you harness 40 collaborators to which, you had even said, typically we work in competition with each other.
Right.
How do you change that paradigm so that you all are working towards a common goal that is funded through a single agency?
Well, Kerri, it is a big shift, and it takes a lot of time, a lot of phone calls, a lot of emails. Fortunately, I've been in this area or this field for quite a while, and I've been funded by the Defense Threat Reduction Agency or DTRA for a number of years. So I knew a lot of the current investigators and some from other fields. And so I particularly looked for people I knew who would work well together. Because you can pull these people together and fund them, but if they're not willing to actually put in the extra effort to collaborate and to get into the biweekly meetings and to share material, share models, share data, it doesn't work well. And so I was very cautious to pull in people that would actually work well together, and it's proved to be extremely valuable. I'm thrilled with the team we have, with the leadership on the team, and I think the industry is excited too at what they're seeing. They really see people working together because they come on, their program managers come on to our calls and they say, okay, well, let's listen to what's happening, and they can see us working together.
So I think that's really for anybody who's sitting in a science class out there, it's an important thing to note that as the field of science grows, the collaborations grows. So all of those skills of collaboration, working together, being able to come to a table and agree to disagree respectfully and actually work towards a common goal, I think they're probably more important now than ever, with MSEE being a relatively new research program and really starting and looking forward to almost a decade of research yet to come.